poor precisions.
You're still on mute, Leska.
Oh, sorry. Okay, thank you. Well, we are at the top of the hour. Good morning, everyone. Welcome to the NDOT Research Payoff Webinar Series. So today's presentation is titled Nebraska Ultra High Performance Concrete for Bridges. My name is Lieska Halsey. I'm a research engineer with the research section here with the DOT. Today, you will hear from Dr. George Marcos from the University of Nebraska. Dr. George Marcos will present the various NDOT and federal highway sponsored research projects from the last 6 years, from developing a non-proprietary USPC mixtures to bridge construction implementation. Also, you will hear from our technical lead advisor from all these projects, Fouad Jaber, from our bridge division. He will provide NDOT perspective on the NDOT roadmap for USPC. But before we start, I would like to go over some housekeeping items. If you will please mute your microphone and turn off your camera, that will appreciate it. Also, we will have time at the end of the presentation to ask questions. But in the meantime, if you have any questions, you can be able just to put them in the chat. Also, at the end, you can be able just to unmute your microphone and ask questions, but that will be towards the end of the presentation. So before we start, so now I will have Fouad to be able just to introduce the NDOT perspective on USPC. So I will start sharing the screen.
Good morning, everybody.
Okay, so
Good morning.
do you see the presentation mode?
Yeah.
No, Lieska, I think you need to change the setting. It shows in the presenter mode, yes.
Okay, now?
I can read it. No, just kidding.
No, now it's gone.
Oh, okay, so one moment. So now?
Nothing yet.
No, nothing's showing.
Not yet.
Yeah, now it is right.
That's good.
Go ahead, Fouad.
Okay. Thank you. Good morning, everybody. I'm Fouad Jaber with the Nebraska DOT the Bridge Office. I'll be responsible for the research engineer and the technical activities. I just want to give a little bit of perspective on US, how we, Nebraska DOT and Bridge Office started the USPC. Just claim 5 minutes here, then we can go to George. I mean, about 20 years ago, or at least close to that, we were in AASHTO. We heard the presentation from FHWA about this exciting material, new innovation in Europe. And we thought, he said, how exciting we have a material reach, we call it ultra high performance concrete, reach compressive strength of about 30,000 PSI. And the most important thing is the tension of it, which is reach up to 1,500 PSI. We thought, wow, that's be great. And how about if we can use it to Nebraska? And here, since we have the people in the University of Nebraska are the leaders in the country, I'm going to just say Dr. Tadros and Dr. George Marcos and Dr. Ma. So these three guys, we thought we have the brain, let's bring the technology to Nebraska and train our contractors and our engineers for the future. So really that's the whole thing started. So that's our vision 20 years ago then, and we are working with this as we go. Go back a little bit, please. So as I mentioned, 20 years ago, the FHWA started this program, and they were doing research in the United States. We participated in a few programs since then, with Everyday Count with FHWA about using UHPC on ABC project, and the longitudinal and the joints, mainly that, and the repairs. So we joined like the EDC 6, ED7 with the repairs of the girders, repairs of columns, and any concrete, which is this material. Since then, PCI published guidelines on UHPC on how to design and how to mix pre-stress for pre-stress girders, and how to use it. That was in 2022. And then follow that, AASHTO published the first in the world, really, from the United States, a guide specification for designing structural element using ultra high performance concrete. As a matter of fact, the University of Nebraska with George and Nebraska DOT, we were on the committee to publish this publications. So we were excited to push this direction, and now we have some kind of code so we can design our structure element. Right now, we are still working with AASHTO to work about the using with the material section of it, to how to qualify it and to do some the acceptance of the material. But that's remained to be coming. George will probably can mention that in the future. So our vision, go ahead, Lieska. So what we have done is really we divided our vision when we discussed we're working with the University of Nebraska Partnership and FHWA, obviously, into two parts. See how we can use this material, innovative material, and the precast application. So, and it is, everybody knows that we do that in the yard and the precasters. So we developed obviously our own called Nebraska mix, using Nebraska aggregates material in Nebraska. So our vision is to hopefully, we did now the beams. We have a section and we have the decked I-beam with Nebraska. We're already doing that. We're working on the piles. We have maybe standardized using the UHPC. And eventually we'll go to the deck panels. Well, that's really work in progress. And the other side said how we establish our own also mix to use it in the field with the contractor mixing. This is for the joint connections of the bridges, the repairs, and obviously, and now underway, we're going with the overlays, using overlay UHPC. And obviously the link slab, which is this is the stuff we can replace our deck expansion joints so they don't leak anymore over our girders. So we're looking, this material is very durable material. Chloride doesn't penetrate it. We thought this is excellent material to restore our infrastructure in Nebraska. So finally, and I'm going to just go back to what we've done so far and the two sponsors research. And we did that in both bridges in 2017. As you mentioned, we already did our Nebraska mix. This is what we have now. We can use that. We're training our contractor, our district engineer, and M&R to do whatever it takes to accept this material in the field. We did participate in precast deck girder connection. We have that already. We have now decked I-beam already in the mix. We already let the project to be constructed soon in this year, I believe. We have sponsored how do you do the production of cast in place UHPC and bridge application, and really this is what we need to train our contractor. And this is work in progress. We're working with our contractors, we're working our district engineer, and we work with our engineer to get this elevation material in the field. Also, we have a repair strengthening material. This is what in place now. We're gonna to try to use it to repair end of girders of any structural element deteriorated fast, and so we can use this, and this is going to be good for the future. And obviously, we have the performance. We sponsoring now. After we get all this element in place, we need to really to do the performance. How we going to do in the future, collecting data to how we can improve and improve and improve. So that's what those are. The research we've done so far, and more to come, I hope, when we get this. So implementation wise, and implementation is very hard. It's always good to have research, but we come to implementation, that's really the elephant in the room. But regardless, we try to get our hands full, and we did UHPC and the connection in the Primrose project in 2014. And that was successful. We partnered with FHWA on that, EDC count, everyday count. We did the transfer joint under ABC project. We finished the project in 30 days using UHPC, and that was built in Laurel 2018. So far, we have in the book with the precaster, actually from South Dakota, Gage Brothers, using UHPC decked I-beam. This is our hopefully, if we go on, if this is successful, we think it's gonna be our maybe standard section, or we can improve on it later to see how it goes. But anyway, this project is running right now. We're gonna build it this year. We'll see how it goes. And obviously, we have now under repair to use UHPC in the detailed pier columns and the girder. This project is already in the books. We're working on it to see how it's gonna perform, and the contractor we're gonna teach the contractor in the field how to mix it, how to perform all this mixing procedure with the help of University of Nebraska. So in general, I'll give you a little bit taste what we have been doing. So, and we are excited of this innovative material to bring it to Nebraska. I think we are going slowly but surely, and I think this material is going to be here for hundreds of years. So I thank you very much for your attention, and I give it back to George and Lieska. Thank you.
Thank you, Fuad. So now, Dr. Marcus, is sure you can start this. Thank you.
Do you see the screen, full screen?
Yes, thank you.
Thank you, Fuad. Thank you, Lieska, for the introduction. And I will be giving you a kind of overview on multiple projects that Fuad mentioned over the last few years that NDOT sponsored. And in these projects, I did not work alone in this project for sure. I had some professors, Dr. Hu and Dr. Tados, were co-investigators in some of these projects. And we had a group of graduate students that did a great job in getting these projects completed on time and published the results as well in articles. So I would like to acknowledge their contribution. So I will go first about introduction about what is UHPC, how it's defined, how it's different from conventional concrete, and then go a little bit more in depth in the properties of this material, because the difference in properties will also make the design done differently, and also the construction done differently. And then I'll go over the applications that some of them, those that Fuad mentioned in the last slide, but we'll show also the research work done at the University of Nebraska, sponsored by the DOT, in order to make sure we are using it the right way, we are getting exactly what we are looking for. So I'll group them into connection joints, and then structural component, repair and strengthening and overlay, and then we conclude at the end with a summary of what was done. So if we would like to look at the definitions of UHPC, the Federal Highway Administration did define it, as you can see in the screen here. It is cementitious material, has the same ingredient of conventional concrete, but the gradation of the particles is different. So it's optimized in a way that minimize the poor structure. So by doing that, you get a material that has very very low permeability or very high resistance to penetration of any liquids or contaminants. So that's what gives it that durability aspect, which is the most important one. And in addition, it also has high percentage of discontinuous internal fiber reinforcement. So this reinforcement, as you can see in the picture here, is the fibers is a specimen that being pulled in tension, and you can see these fibers sticking out of the concrete or bridging the gap between the two parts until failure. And you can see the cross section, all these little dots are pretty much the fibers. So it's a high percentage of fibers that provide tensile capacity of the concrete even after cracking, and that's the main point. So you don't want just the concrete to lose its capacity once it cracks, but it also can sustain. That's why it's called sustained post-cracking tensile strength of at least at the minimum 750 psi. Most of the time we get higher than that, 1,000 or 1,200 or even sometimes 1,500. The compressive strength is also high, and that's pretty much a kind of a byproduct from having optimized gradation. So once the mix is intense in terms of the packing, particle packing, and has very little void, it also helps the compressive stress. So this is a definition by the FHWA, and before that there was the first ASTM that was done in 2017. That's ASTM C1856. Up till now, that's the only ASTM standard for UHPC that describe how to fabricate a specimen and how to test them to make sure the properties are met. They also add in the definition a little bit more information regarding saying the nominal maximum aggregate size is less than 5 millimeter or a quarter inch. So it's pretty much UHPC doesn't have any coarse aggregate. It's only sand and all the powder material. It also adds a statement that is not in the FHWA definition, which is having a flow from 8 to 10 inches measured using the flow table test that I show on the screen here. So it's a very flowable material. It's like self-consolidated concrete type of material. So you don't need to vibrate it. You also gain ability for this material to flow and fill very tight spaces between reinforcement or strand, or require very small cover because it's highly durable, and at the same time it is also very flowable. So as mentioned also earlier, that currently the PCI completed a 3-year research project from 2019 to 2022, and published a long report showing the different types of application for UHPC, not only in bridges, but in bridges and buildings. And also they published this report that give guidelines for precasters, how to produce UHPC and how they do the quality control. And then after that, recently, a year ago, the FHW, AASHTO published the first document, which is about guide specification for structural design using UHPC, and it's not covering everything like regular AASHTO LRFD, but it covers enough for the DOT to start making components using UHPC. And as you can see from the picture, even on this cover here, you see how thin the web is. And this web is with UHPC, you don't need to add reinforcement. You don't need even to add reinforcement in the bottom flange or top flange because of the fibers that are within this material and give it some kind of reinforcement. So it can basically reduce significantly the amount of conventional reinforcement in concrete. Just to give you an idea about this is about how widespread the use of UHPC. This is a map from the FHWA website that shows the different projects and their distribution across North America. And it shows how the project increased recently, specifically in the last 3-4 years, with a large number of projects in the East Coast, especially in New York and New Jersey, and some in the Midwest in Iowa and also Nebraska. And the distribution of these projects, if we look at how these projects are distributed with respect to the type of the project, you'll still find that the number one application of UHPC that represents 77% is the connection between the joints of precast pieces. So that's the most common application. And then after that is the use of link slab to replace the deteriorated expansion joints. Do you hear me well, Lieska, or we got disconnected?
Yes, we are.
Okay, just checking. Thank you. So the most common application after the connection is using link slab to replace expansion joint, using an overlay to protect the bridge deck. Very little work done in developing precast pre-tension components like girders or piles, and also very little application till now in repair of components. And that's what we see a big potential in expanding on those, and that's what Nebraska is currently doing. So to present a little bit more information about what are the constituents or ingredients of UHPC, this is a mix that was developed 6 years ago using local material in Nebraska, and that's the composition, and that's kind of schematic presentation showing the particle sizes. So the largest actually particle size is the fine aggregate. So you have a fine aggregate number 10 sand, that's the majority of the mix. Comes after that the cementitious material, which is cement, and it has slag and silica fume as supplementary cementitious materials. In addition to that, of course, you have water and admixtures, and the amount of water is very small compared to the amount of cementitious material. The ratio is less than 0.2, which is very low water cement ratio. However, with the use of high range water reducers and workability retaining admixtures, this allows the material to pretty much be very flowable and maintain its flow for a significant amount of time. And of course, the most important component for the tensile behavior of UHPC is the fibers, and I show a picture here to give you a sense of how big. These fibers is 1/2 inch long and a very, very small diameter, 0.002 millimeters. So it's very small diameter, 0.02 inches, sorry. Here's just showing you some of the properties that you get from this mix. This is results from a mix that was done actually not in the lab. This is not a lab mix that we do a small batch, but this is done at one of the precast producers in Nebraska. When we did one of the specimen, they did large quantity, about 6 cubic yard of UHPC, and we did the testing for them back in 22. And you can see the compressive strength grow significantly, and even after 56 days, it's still going up, and we reach over 21,000 psi compressive strength, much higher than what you usually get from conventional concrete. And it is actually showing you the failure even of the specimen under that high load. It does not have the same conventional failure that you get when you test the cylinder. You don't form a cone or big cracks, or you get it completely fragmented, but you basically get just the cracks and the fibers holding it together. You can see also the fiber distribution across the section. That's what gives it the ductility that you need and prevent it from having a sudden failure. Also, sorry, I pressed a couple of times. Another test that is very important for UHPC is the flexural test, which is pretty much is a 4-point bending or third point loading, where you have a prism made of the UHPC and loaded at 2 points in the middle. And this is a kind of a 12-inch span, a 14 inches prism, but 12 inches span, and it's a 3x3 or 4x4. There are two types of prisms, and you test it, and not just looking for the maximum load that breaks it, but we're looking for the entire load deflection curve. So here's the stresses, flexural stresses, and the deflection. And you can see here what exactly happening. After it cracks at this point, it's still carrying load until it reaches a peak. And even after the peak, it still has some residual capacity. So it does not break. And that's the function of the fibers that are bridging the gap once a crack occurs. So you look at this material, you evaluate it with respect to the cracking stress, which is the first line here. According to PCI, it requires to be more than 1500 psi, and the peak should be higher than 2000 psi. And also looking at the residual stress at L over 150 of the span, which is 0.08 inches. So it requires that this to be at least 75% of the peak. And as you can see here, all the specimen we tested for the mix developed in Nebraska meet these requirements quite well. Another property that we look at is the tensile capacity. This is a test that developed recently by the AASHTO, by the FHWA, and approved as an AASHTO standard test, which is called the direct tension test, in which you make a prism. As you can see here, these are 6 prisms. They are 17-inch long, 2x2 inch in cross section, and you grip it from top and bottom, and you pull this specimen while instrumenting the middle third of the specimen to see the strain. So pretty much developing stress strain diagram the same as you do with a strand or steel bar. You do that with concrete here because it's fiber reinforced concrete. So you also look at when it first cracks and then how that increases capacity even after the first cracking, and that's what they call it strain hardening. So if for regular concrete, once it cracks, it drops immediately. But for UHPC, because it's fiber reinforced, once it cracks, it still gain some capacity and carry more stress before it starts going down. And that's what's called the strain hardening. So it has to be a strain hardening material to be accepted for use in a bridge component, according to the AASHTO. And you look also at the strain at which the first crack enlarge and become localized, like what you see here. These are the localized crack that you see very big. There are a lot of hundreds of very fine cracks, but there is one of them that opens, and that's when the fiber starts to pull out of the concrete. And that's what we label as localization. So this is a very important criteria for structural design using UHPC to know when does that happen. So if it happens at a certain strain, that's called localization strain. And also we look at the localization stress as well. So these are the mechanical properties that are very important to test for, so you can know if UHPC that you have and you're going to use meet the requirements according to AASHTO or according to a specific project requirements. So after that, there's also something very important, in my opinion, for UHPC. It's not just a mix and adding the fibers. You want to make sure that the fibers are stable in the concrete. Very similar to the idea of having self-consolidated concrete, and you want to make sure the coarse aggregate is well distributed and stable in the mix. So This is still not, there's no standard test to do that, but so far we evaluate that visually using what's called visual stability index by looking at the shape of the material once you do the flow test, and see if the fibers are well distributed, or there's any separation, or any kind of agglomeration in the fibers. So you can see the top one here is like very highly stable. That's visual stability index 0. This one has a little bit, that's considered 1. Now when it starts forming like this, that's unstable. And of course, 3 is highly unstable, and 4 is like that. This is very important to know, that the mix is very stable. Otherwise, you lose the advantage of having fibers, because they are all in one place but not in the other. So you're still gonna get very big drop in the tensile performance. Here's also showing you that as well in a different way. Sometimes we look not just at the spread only, but also how fast it spread or reach that spread. I'm going to run a video, but I just want to make sure the sound is low, so it does not cause. So here's a very stable one. You can see it takes time to spread and fill the table, the flow table, which is 10 inches diameter. But that's an example of a very stable UHPC. But the other one here, which is not as stable, you can see what happens here. It just flows very fast. And that means it doesn't have enough viscosity, and you get some separation of the fibers. This is very important during construction. At the plant itself or the site, you do that test before you cast it in the form. Make sure it's flowable enough and stable enough. You can also detect that later if you make cylinders and slice them. You can see this is a stable mix on the left side, where all the fibers distributed equally from top and bottom, but there's one next to it on the right has a very big part of the top that is not doesn't have any fibers, and all the fibers are pretty much at the bottom. This is not acceptable in this case. One other thing that is important for UHPC to know is that it's a material that has a lot of cementitious material in it, and that makes it also shrinking a lot. So you need to understand that this is of course it's a risky thing, but at the same time there's a solution for that. So some materials, when they are designed, some UHPC, when they're designed, we add to them specifically shrinkage reducing admixture or shrinkage compensating admixtures, and this pretty much lower the amount of shrinkage that happen to the UHPC to the normal levels you get in any regular concrete. So if you can see that the black line here shows a shrinkage that goes to up to 800 microstrain, which is pretty much a high level. But when you use different types, I'm not going into details of what these products are, but these are different products of shrinkage reducing admixture or shrinkage compensating admixture at different dosages, and it shows you can get it basically to half of that amount if you use the right material and the right dosage. And we did that evaluation to the mix developed here in Nebraska to make sure we understand how it behaves in terms of shrinkage. So that's the first part is mainly focused on material, to give you a brief overview on how it is different from conventional concrete with respect to flexure, compressive strength, tension, and shrinkage, as well as fiber stability. Now let's go over some of the applications. I'll start with the two projects that were done back in 2014 and 2018, when a commercial UHPC was used. That's before we developed our own UHPC. And that's the Primrose East Bridge, where they use the UHPC for connection between precast segment. So in this project, it had a folded plate, steel girders with a cast with a conventional concrete deck on top of it, and also diaphragm. So we make these girders 57 foot long, and they had, I think, 4 of them, and they put them side by side, and then used UHPC to fill the longitudinal joint between the segments. And this is a picture here how the segments look like. And UHPC was mixed on the site using portable mixers, and then cast at these joints, and then covered to make sure it does not flow, because you might have some slope on the bridge. So to show that it's all leveled, and it filled all the joint. And one thing you notice here is the joint itself is very small. So you don't need a 2 foot or 1.5 foot joint between the pieces. I think this was 8 inches, and the bars from each segment is about 5 or 6 inches, because UHPC allows bars to be developed in a very short distance, about 8 times the diameter of the bar. So a number 5 bar can be fully developed in 5 inches. If number 6 inches. So it is very efficient in reducing the size of the joint and the quantity of concrete and how much the bars need to be projecting out of the precast piece. The second project was done in 2018. That was building a Laurel Bridge. It's a simple span, 130 foot long, 7 NU 1100 girders, and has also precast deck with a rail. So the whole bridge was a precast, and we used UHPC in the transverse joints between the deck panel as well as the joints between the rail. So this is where the UHPC was used, the transverse joint and the rail joint. And again, the joint was very small in width, and the bars sticking out were very short as well, 5 or 6 inches. So I think I have a video here as well to just show that without the sound. So that's how UHPC was mixed using on-site mixers, portable mixers, and then wheelbarrow to cast them in the joint. They put plywood on the side of the joint, so they can also cover it from the top to have a top form to make sure it does not flow outside the joint, because the bridge has a slope, across a slope about 2%. So you have to form it from the top as well. Now, these are the recently developed applications for UHPC in Nebraska after developing our own mix, as I explained earlier. So one of these applications is developing a decked I-beam. The advantage of having a decked I-beam is that you have one segment that all precast, and you don't have to cast in place a bridge deck in the site, so it allows accelerated bridge construction. So this was one of the early versions of that section. Is there any questions or comments? Okay. Please write any questions or comments you have on the chat box, and we can go over it at the end of the presentation. So this is one of the early versions of that system, and it was modified a few times until we have the final version that will be constructed produced this summer by Gage Brothers in South Dakota. So that, as you can see here, it's very similar to an I-girder, but with a full width top flange that pretty much 10 feet or whatever the spacing is. And the nice thing is that deck slab is not a solid slab. It has what's called a ribbed slab. So it has very thin skin, which is about 2.5 inches average thickness, and it has openings between those. So that's why the form is a little bit different and challenging, but using UHPC allow to do that, and by doing that you reduce significantly the weight. Also you reduce the thickness of the web, as well as the thickness of the bottom flange. So you end up with a section that uses less material, has less weight, so it can allow for say more live load for the same weight of for the same spans and same spacing. Here's the picture of and a drawing of the specimens we did in Nebraska before we go into this project. We did a couple of specimens to check the performance and the production of this kind of section. So that's a specimen that is 20 foot long, 10 foot wide, with a form here. You can see the pans used to create the voids, and you have the ribs between the voids, and the ribs are the only part that has reinforcement. All the rest, no reinforcement except the pre-tensioning strands. So that was done. Just show you some also pictures. Sorry, I just don't have a loud noise. So this is the mixing in the precast plant, and you can see the fibers were added after the mix became flowable. That's how you do it. You mix it until it becomes flowable, and then you add the fibers in the concrete, so you get it only well distributed, and it flows the concrete pretty well. Here's another one that shows you when they were casting it, showing how flowable it is, and it can fill the bottom flange, the web, and then in the top it filled the ribs between the pans. So it's very well stable and very workable mix. So this is a segment that was produced, the pre-tensioning strand at the bottom, dropping the top flange form, dropping the pans, and then shipping it to the lab for testing. That's how it looked. We did few testings, and these are all in a report of the project, but I just will show you one test, which is the loading it to see the punching of the top flange, which is a ribbed slab, and how it performs. Does it have enough capacity for the wheel load from the truck or not? This is a cross section. So here's a cross section of the deck itself with a ribbed slab, and there's a reinforcement top and bottom, and we were able to load it with over almost 76,000 pounds before we had a failure, and that gave a ratio between the load to the ultimate load, the factory ultimate load from the truck to more than 2. So it can carry twice the capacity you design for even for the factored load. And it shows here the failure, how it happens, pretty much like punching shear at the edge of the slab here where we put the load. So the UHPC worked very well in terms of without even reinforcement in the skin, having the fibers give it very high resistance to punching shear, and it performed way more than needed. We did also, as a part of the project, we were experimenting of production at the other precast producer for bridge girders. So we did another specimen. This one we were exploring if we can do a bridge girder using segments that are post-tensioned. So it's a different system to allow the contractor to have options. Either can do pre-tensioned or can do segments that are post-tensioned. And in this specimen, we also experimented the use of solid slab that is thinner than regular. In regular deck slab, we do 8 inches. This one we did 6 inches solid, and we also did testing for it. So as you can see, the production as well went very well, very flowable, and it resulted in the cross section that you can see here in the bottom right corner of the slide. That's when it's ready for shipping to the lab. You can see again the thin web and the location for the duct, for the post tensioning, and the solid slab that is 6 inches only. We did similar testing for that as well, and it performed even better than the previous one. Performed very well. Get a capacity, a load punching load capacity to the demand. The ultimate one is more than 3.2, and it did very little cracking on the side and the bottom of the flange. So these were very successful specimens in terms of production-wise. The producers were able to produce larger quantity, over 6 cubic yard of UHPC in a very efficient way using Nebraska mix, and also give them experience on how to deal with such a material and the forms for digged I-beam. This is some information about the bridge project that is being planned to be produced and constructed this year. It's a 3-span, 75, 85, 75, and it will have 4 girder lines in each span, so a total of 12 girder lines. This is a cross section, and here is a cross section of the beam, the digged I-beam with ribbed slab, and it will be produced using the same mix we just presented. Okay, let's look at some other applications for UHPC. Just want to make sure I don't take all the time in the presentation and give you some chance for discussion and the questions. So I go briefly over those. So there are many applications for UHPC in repair. We looked at some potential projects, either a bridge pier repair, pier cap repair, bottom of the column, or with a foundation part here, deterioration at the bottom of the column, expansion joint that we talked about earlier, that using link slab instead of having a deteriorated bridge deck at the expansion joint, as well as the girder ends and the pier cap here. So these are all actual projects that have a big potential to be successful implementations for UHPC in repair. Within the research project, we looked at different ways of using UHPC to repair, and one of them is trying to strengthen and shear by adding 1.5 inches or 2 inches of UHPC around the web of an I shape. This is, of course, a scaled specimen. This is not a full scale, but it was just to evaluate how much capacity we can get when we cast UHPC around the web. So we added some anchors, mechanical anchors, form it for the 1.5 or 2 inches of UHPC, made holes in the top flange so we can cast from that, and we end up with a cross section of the strengthened girder that looks like the bottom picture here. And then we tested those. So we tested those girders in shear, and we get some. We get actually here tested 5 girders. The first one is the black line, is the one before strengthening, and then we had 2 strengthened using 1.5 inch additional web, and the other 2 is for 2 inches, and you can see a significant increase in the capacity in shear by adding only 1.5 inches or 2 inches of UHPC around the web. And we didn't notice any kind of delamination or separation between the 2 materials. And so that was a very successful application. Excuse me. Another potential use is to strengthen in flexure by adding UHPC at the bottom of an existing girder in case it need to be strengthened for lifting the load restriction in a bridge, especially if it is reinforced concrete, not pre-stressed one. You add some anchors as well, add some reinforcement around the anchors, put a kind of a tub at the bottom flange, fill it with UHPC, as you can see, and you can get a cross section that has additional 2 inches of UHPC with some bars that can also increase the capacity significantly. We looked at this, tested in flexure. The black line is again the original, the reference, and then the red one is when we added 2 number 6 bars, and then the brown one is when we added 3 number 6 bars. You get UHPC to act as a composite section with a conventional concrete, and the new bars contribute to the flexure capacity. So that also is a very successful investigation. We looked at how you can encase existing columns using UHPC. So we built few specimens, and some of them was sandblasting, others was after removing the covers and then formed around those and added 2 inches of UHPC all around the column. Again, here's just let me take the sound off. So this is how we form around the column, adding a UHPC. That's how it looks in the picture here after adding 2 inch all around. Some specimens done with sandblasting, surface preparation, others with removing the cover. In some cases, we added additional confinement reinforcement. So to look at how this will perform when we apply axial load to see how much increase in the capacity we get. So here's a summary of the results that we looked at. So we looked at 2 specimens with sandblasting surface preparation, others with removing the cover, and 2 of them was adding also additional tie reinforcement at the top. So axial capacity is supposed to be 293. That's for the original one, and after adding this UHPC, we ended up with increasing the capacity significantly. And actually, for the last 2 columns, we stopped the test because we maxed out the capacity of the loading frame, so it can even go further than that after adding the reinforcement at the top. And the reason we decided to use reinforcement at the top, because in the first specimens we found that we get crack at the top, so we added additional reinforcement that helped significantly increase the capacity. So we're exploring what is the best and most efficient way to use UHPC, even in conjunction with adding some reinforcement, if that will help improve the performance. So one of the last applications is deck overlay. And I would like to mention that when you use UHPC in deck overlay, we need to look at a different type of UHPC, not the same one we use for structural components or for repair. And the reason is because when you added a thin layer of UHPC on top of a deck with slope, you don't want it to be basically moving and change the thickness from one place to the other. You want it to be stable, and you cannot top form it. So you need to make a special kind of UHPC that is called highly thixotropic, which means if you don't agitate it, it stays stiff, but if you agitate it or vibrate it, it basically continue to flow. So that's required changing the mix or developing a new mix that has high thixotropy and also has workability retention, in addition, of course, to having good bond with the existing concrete. So this was the picture on the left is the one we presented earlier. But we, for UHPC overlay, we did another mix that doesn't flow under static testing, but it can spread and flow under dynamic testing. And that's a different type of behavior that is needed for that application. And we looked at different ways of surface preparation. So if we talk about a new bridge deck, we can do a surface retarder, so we can expose the aggregate. If we're looking at existing bridge deck, we can do milling, and we try two different patterns of milling, the typical one and the finer one, to see how much bond you can get with UHPC when you do this type of milling. So we did the specimens, and we developed the mix first, and we cast it at 2% slope. And let me just show you a video. And we used a vibratory screed to spread it. You can see how stiff it is ahead of the screed, but before it flows very well and leveled very well with the vibratory screed. And that's what we really looking for, to have a static spread of less than 6 inches, but dynamic of about 8 inches, 7 or 8 inches. So we did that with a mix that has low powder and 3% fiber, and then we did it again for a different mix with high powder and 2% fiber to give the DOT two options and see the performance when we change the dosage of fibers and the powder. So we did that experiment, and we also tested them if you cast them on top of a conventional concrete deck, and we tested in flexure, and then we flipped the specimen to keep the UHPC at the bottom, so we see the negative moment zone in the bridge deck, how it performed. So we evaluate the capacity in positive moment and negative moment. And we did that for multiple specimens with different type of surface preparation, whether it's a surface retarder or fine milling or typical milling. And we looked at load deflection or capacity deflection diagrams. And in all of them, we looked at the experimental value and the calculated one and the ratio between the two, and we always exceed the predicted capacity or even the capacity for a conventional concrete, normal concrete slab. Significantly increase the capacity in positive moment and also in negative moment. Here's the one. And just to show the failure here, when you have a positive moment, you just fail the conventional concrete by cracking it and yielding the bars. And the negative moment, because UHPC in the tension, you get the crack localization, and you see the fibers bridging the gap until they completely pull out of the concrete. So we expected that behavior, and we saw that in the testing. So we're very comfortable that it behaved as predicted. So I will summarize the presentation by giving few conclusions here, so we can have some time for discussion and question. So there are a lot of applications for UHPC and bridges all over North America, and that's pretty much because designer realized that it has strengths and durability and workability, also properties that makes it easy to cast, and also to reduce the life cycle cost for bridge maintenance and repair. We developed a non-proprietary mix using local aggregate, local material in Nebraska that ended up with having a mix that pretty much a quarter the cost of the commercial one. When you produce UHPC, you need to give it some additional attention. It's not as easy as it is for conventional concrete, because it's more steps. It takes longer time, for some special sequence, but you need to also, most important, to make sure it's consistent, stable for the fibers, well distributed, and avoid having cold joints, because if you're going to have a cold joint, you lose the advantage of the fibers being a tensile reinforcement across this joint. So it needs to be continuous casting. if you use UHPC for bridge component, the sections need to be redesigned. So you don't use it for exactly the same section used for conventional concrete. Whether it's a girder or a deck panel or a pile, need to be redesigned to be to make advantage of the UHPC and the elimination of conventional reinforcement or minimization of conventional reinforcement. For repair, it's an excellent repair material for beams, columns, slabs, in shear, flexure, and axial. And we have seen that in all the examples we made in the lab and tested. For being used in an overlay, it needs to be a highly thixotropic UHPC, and it can be used with surface preparation, either with exposed aggregate for new bridge decks or using milling for existing ones, and it create a very good bond, and it was very successful in both positive and negative moment testing. Okay, so that's what I have, and I thank you for your attention, and I'll be glad to discuss any of these projects or any questions you might have.
Does anybody have any comments, or even if it's just any comments?
We have two in the chat. The first one is, has NDOT reached out to AGC for training and field application?
I think that's a question for the DOT, not for me. But I give a presentation before in one of the AGC meetings, and we did a few years ago. We did a kind of a workshop at the university, a full day workshop, and it was well attended. We had over 40 participants. Some of them are designers, others are producers and contractors. And in this workshop, we spent half of the day in terms of giving a presentation, answering questions, and the other half, we did a kind of a lab demonstration, show them how to mix UHPC, casting it, and testing it. So it was a good experience, and we, I think we will be happy even to do it again if needed for training and for educating the contractors and their staff.
Okay, and the second question, what was your experience with keeping fibers evenly distributed? Are there best practices for a stable mix?
Yes, we have a lot of experience on that. And a key parameter here is the keeping the water cement ratio within what is specified. And that it's very sensitive to any changes in the water content in the mix, because once the water goes above what is supposed to be, and we had some bad experiences with that, people add water just to get it flowable faster and think that this is going to speed up the production. It resulted in lowering the viscosity, and once the viscosity is lowered, steel fibers, steel in general, have higher density unit weight than concrete. So once you lose the viscosity, the steel starts moving down. So controlling the water cement ratio is very important, and that also involves the water in the aggregate. So if the producer did not measure accurately how much moisture in the aggregate, that basically change the amount of water in the mix, make it less viscous, end up with the fibers basically settling down and not being well distributed. So water content and moisture content in the aggregate are very important to be controlled. And it's not a big deal. It's not a problem. You do it stiffer mix at the beginning and then adjust the workability using admixtures later. But when it happens the opposite and you get settling of the fiber, that's a bigger problem.
Have a few more. Did the fabricators encounter any difficulty with equipment or cleanup due to the fibers?
The equipment, they use the same mixers they use for conventional concrete, but at a lower capacity because UHPC require more energy for mixing and longer time. So if they used to batch in the mixer 6 cubic yard mixer, they used to batch 6 or 5.5. Now they have to go to 3. That's one thing. But they use the same mixer but a lower quantity. And if it used to be mixed in 5 minutes, this one takes maybe 20 minutes, so longer time. About the cleanup, yeah, all what happened is they end up with some leftover fibers. So they might get some fibers in when they use the mix for the next batch, but I don't think they complained too much about it. And having some fibers in the concrete is not a bad thing. So yes, it took a couple of batches to get rid of all the leftover fibers stuck with the mixer and the shaft.
Okay. In the case of the overlay, what is the surface friction?
Okay, we did a specific test called the bonded test. I didn't have time to show that. We have equipment where you go and do a core, and this 2-inch diameter core, and then you glue a steel disc on top of the UHPC and then pull out and see where the failure happened. If the failure happened at the interface, that's a bad thing. You want the failure to happen in the conventional concrete, in the substrate itself. And we measure the load over the area to get how much bond strength we have. So we don't measure in terms of friction, but we measure it more in terms of bond, because you don't have reinforcement crossing the interface. So friction is not really the important thing, but the bond itself with the adhesion itself is more important. And we get very good results with exposed aggregate in the range of, I think, a range of 300, 400 pounds per square inch in terms of adhesion. And with milling, it was less, in the range of 200. And the literature shows that if you do even hydro demolition, you get even better, the range of 500 pounds per square inch. So we evaluated that parameter for different types of surface preparation.
What happens when exposed steel fibers rust?
Yes, this is very common when you have a form. After you move the form, there could be some fibers, ends of the fiber are showing, and this causes a little rust stain, but it stops there. It does not propagate inside the concrete. Because if you recall, I mentioned earlier, the mix is very dense mix, and it has a very discontinuous and small pore structure, so doesn't allow moisture to go through. So it's very impermeable. So the stains shows at the surface and then it stops. And they have the Federal Highway have tested a lot of UHPC specimens in a very aggressive environment for a long period of time, and they found, yes, it stops only at the rust stain you see at the surface, and that's it.
Okay, and the last question we have in chat is, what is the expected minimum and maximum thickness of UHPC overlay?
We have seen from the projects done in New York and New Jersey, did a lot of these projects. They are the most popular place for UHPC overlay, and it ranges from 1.5 to 2 inches. I don't think there's any problem of going more than 2 inches if they want, but of course it's expensive. Going smaller than 1.5 inches, I think it might be still okay. The only problem will be how accurate you will do it, because you're still gonna get some tolerance, plus or minus. And when you have fibers, you don't want to that are 1/2 inch long. You don't want to go very thin, because you will not have the thickness has to be at least 1.5 times the thickness of the fibers. So they say the minimum thickness for a 1/2 inch fiber is a 3/4 inch, but plus or minus also the tolerance. So pretty much you cannot go below 1 inch, assuming there is also some tolerance. We did before in the lab some panels that are 1 inch thick, and it performed fine in terms of flexure. So you get a good performance from 1 inch as well. Is there any new ones?
No, that's the end of the questions in the chat. And so any other final comments or questions in the group? Oh, Dr. Don't see.
We still have
Yes,
like
mhm.
3-4 minutes. So if somebody wanna use the mic to ask questions, this will be okay.
Yep.
You can stop sharing.
So it seems like a pilot project for an overlay would be interesting to get rolling. What would you suggest for a good candidate for that? I mean, I'm thinking high traffic, not too big.
Yeah, number one, it should, because as you said, as some people ask, the AGC are not very familiar. I don't think we should start with a big project. Like some states, they have that experience and they can go for miles. But I think it has to be a small, and maybe also something that can be staged. So you do a one lane at a time, or one way at a time. So you don't have to produce large quantity, because I don't think contractors are ready for that yet.
I mean, for evaluating the effectiveness over time, we'd probably need to do a few of them, 20 of them or something, to get a small population.
Yeah.
And figure out what works well and what's deliverable for the specifications.
Yeah, and also the surface preparation part. Is it a new bridge that we can add a surface retarder and have aggregate exposed to do the UHPC on it, or it is that would be easier actually than going and doing a deteriorated bridge and trying to mill it or do hydro on it, because that will increase the cost.
Yeah, no, I think a new bridge makes a lot of sense. And also with the thinness of this, it's going to help a lot with our rail heights. We're kind of limited to how thick we can go with overlays due to
Yes.
to preserve the rail capacity. So
Yes.
that thickness is very attractive.
Yeah.
And we have one more question in the chat. Do you foresee UHPC replacing conventional concrete in bridge construction if its use becomes more widespread and costs decrease in the future?
Not replacing entirely, because some some components you need to have a mass concrete. You have large quantity, and the mass of the concrete are more important than the property itself. So I see it for any flexure member. Yes, it can be a good candidate, but I don't see that in full pier or full wall made of UHPC. I don't think we need that, because you cannot reduce the section after a certain amount. So you still need to have a big cross section. You cannot, for example, because of the having the capacity 20 KSI versus 4 KSI, you can reduce the cross section to 20%. You cannot do that. So you will still have conventional concrete, maybe with, as we said, a jacket of UHPC around it, or repair by increasing the web thickness or things like that, but not replacing the entire bridge with UHPC. I don't see that an effective way of designing using UHPC. It has to be optimized.
Well, thank you. Thank you, everyone. We are at the top of the hour, so thank you, Doctor. Thank you for your time and the presentation. Thank you for attending. We will follow up with your PDHs through email, so just be on lookout for that. So thank you, everyone. Appreciate your time.
Thank you, Jessica. Thank you, everybody.
Thanks.
Have a
Thank
good
you.
afternoon.